In the last video, we looked at the critical buckling load for pin-pin column given by Euler's formula pi squared EI over L squared. What happens if the column is not pin-pin but had different support conditions? What about different support conditions? Let's first look at a cantilever column, length L, apply an axial load. Now, if this column buckled, it would have to buckle in a shape that looks like this because the bottom end is fixed, so it cannot translate or rotate. Now, if we extend the shape of this column, just mirror it like this, this is a point of zero moment, and if we look at the mirror image, then we can think of this bottom point also as a point of zero moment. So this entire length twice L looks like the buckle shape of a pin-pin column. Based on this, we can write the critical buckling load of a cantilever column to be pi squared EI over whatever length looks like the length of a pin-pin column. In this case, that's 2L. So 2L squared. Now let's look at another support condition where the column is fixed at the base, but at the top it's fixed against rotation but free to translate in the horizontal direction. This kind of boundary condition can occur, for example, if there were a frame in which the beam is much stiffer than the columns. So that the top of the column is not free to rotate, but it is free to translate if it deflects like that. So let's say we apply an axial load here. Now if we look at the buckled shape of this column, it's going to be like this. And because this is symmetric, the point of zero moment must occur exactly at the middle, so that if the total length is L, then this must be 1/2 of L. Now if we look at the mirror image of that, then that segment looks like a simply supported column. So the critical buckling load of a column with these support conditions is pi squared EI over L squared, because the length that looks like a pin-pin column is L again. Now let's look at a fixed column. Which is free to translate in the vertical direction up top, but is fixed against rotation and transverse displacement. And we apply an axial load. The buckle shape now has to look like this. And because of symmetry, the bottom half must be exactly the same as the top half. And again, if we look at the top half alone, because of symmetry, the point of zero moment must be right in the middle. So if that whole length is L, then the distance between the points of zero moment is 1/2 of L. So the critical buckling load for a fixed column is pi squared EI over 0.5 L squared. So we see that a cantilever column has 1/4 the buckling load of a pin-pin column, whereas a fixed column has 4 times the buckling load of a pin-pin column. Now let's look at a column which is fixed at the base but pinned at the top. If we look at the buckled shape, it's got to look like this, and the point of zero moment must occur somewhere over here, and the length between points of zero moment, or the length that looks like simply pin-pin column, it's somewhere in between L and 0.5 L. It turns out that it's 0.7 L if we did a full-fledged analysis. So the critical buckling load of a fixed pin column is pi squared EI over 0.7 L squared. So we see how this idea works. In fact, so in general, we can write the buckling load of a column of given boundary conditions as pi squared EI over some k times L squared, where k times L is called the effective length, and k is called the effective length factor. So we can see that for the cantilever column, k is equal to 2. For this column, k is equal to 1. For this column, k is equal to 0.5. And for this column, k is equal to 0.7. In fact, the AISC specifications has a chart that indicates exactly this. We see that for a fixed column, the effective length factor k is 0.5. For a fixed pin, it's 0.7, and so on, just as we deduced by looking at what part of it corresponds to distance between points of zero moment. But there's also another row that has recommended values for design. So the effective length factor recommended for design for a fixed column is a bit more than 0.5, and that's because these supports may not be exactly quite fixed. They may have some flexibility. And if they had some flexibility, then the points of zero moment would move out in that direction, increasing the effective length. So effective length, if it's a fixed column, to account for the fact that it may not be perfectly fixed, the effective length factor is conservatively to be taken as 0.65. Similarly, for a fixed pin, it is to be taken as 0.8, and so on and so forth. Now, in a building, the support conditions of a column may not be exactly fixed or fixed pin, but instead, a column such as this may be surrounded by other columns and beams. So in this case, the AISC specifications provide a way by which we can calculate the effective length factor using these charts called alignment charts. But we will not get into that in this course. You will learn much more about effective length factors in more general situations in your steel design course. We've seen that the critical buckling load of a column can be written as pi squared EI over the effective length factor k times the length L squared. Now we can divide both sides by the area of cross-section of the column. And we can write I over A on this side. Now we recognize that the moment of inertia divided by the area is the radius of gyration squared. So we can write this as pi squared E divided by k times L over R squared. And this quantity k times L over R is called the slenderness ratio. So the bigger the slenderness ratio, the more slender the column is, and the smaller the slenderness ratio, the stouter the column is. We also recognize that this quantity P critical over A is a stress, and we can call that the critical buckling stress, FCR. You're probably used to using the symbol sigma for stress, but in the AISC specifications having to do with steel design, uppercase F is used for stress, so we'll do the same, FCR. So we can now plot slenderness ratio and the critical buckling stress. And if we plotted FCR equals pi squared E divided by KL over R squared, we would get a curve that looks like this. As KL over R becomes, the slenderness ratio becomes very large, the critical buckling stress becomes very small. And as the slenderness ratio becomes very small, the critical buckling stress becomes very large. This seems to suggest that we can keep on increasing the compressive stress on a column. But that's not true, because there will come a time when the amount of stress we can apply on the column will be limited by the material strength, F sub y, the yield stress, limited by material strength. So until a certain value of the slenderness ratio, buckling controls, and then smaller than that value, material strength controls. This is in theory, but in practice, the curve actually looks something like this, where there's not an abrupt transition point like this, but a gradual. So this is the compression strength curve. And the AISC specifications, for example, provide an equation for this curve. However, in this course, instead of using the equation for this curve to determine the strength of a column, we will just use some tables that are also provided in AISC as a simple way to obtain the design strength of a column. But in the steel design course, you will learn much more about the compression strength curve. Another point to note is if you have, for example, a column made out of an I section, with the compressive load applied, for bending about this axis, the moment of inertia is larger. So this is the XX axis. And for bending about this axis, the moment of inertia is smaller. So all other things being the same, buckling would occur about the weak axis. So K times L over the moment of inertia about the YY axis will control buckling all other things being the same. So in the next video, we'll look at how to use the AISC design tables to calculate the design strength of columns.